Perfect. Welcome, everyone. We have today a very special part, and this is our panel, Beyond InfiniBand, Migration to Ethernet for High-Performance Networking. And today we have very special guests from Ionos, who took that journey and been migrating from InfiniBand to Ethernet using open networking technology and enterprise Sonic. So let's start with a brief introduction, maybe starting from you, George.
Okay, yeah, thanks. Mic's working, right? My name's George Daly, and I am leading a team called the Data Center Network Fabric team, working for Ionos. We are responsible for the design and build of the network fabrics using Sonic now as the network operating system. And we are responsible for designing and building and rolling those out in our locations through Europe and the US.
Okay, my name is René Mack. I'm a network engineer at Ionos, employed since 10 years at Ionos and since 8 years engaged with network technologies and currently working in a network reliability engineering team focused on automation.
Hi, my name is Kamran Naqvi. I'm based in the UK and part of the Broadcom team.
And my name is Łukasz Łukowski. I am also part of the STORDIS team. Today we are your host. My background is open networking from 2014 with a full, let's say, heart. So, George, starting maybe from a brief introduction of Ionos, I can imagine that maybe not everyone are aware what Ionos is doing and all the services which you are providing.
Yeah, sure. Let me give it a shot. So I'm not a marketing guy, but I'll try. So the Ionos group was founded, I think, around 25 years ago. We used to be known as 1&1. Maybe you heard of that. We had a rebrand a few years back to Ionos. So to give you a rough idea of our scale, from 2024, so last year, total revenue was in excess of 1.5 billion. We have 6.5 million customer contracts and over 22 million domains registered with us. So we're of a reasonable scale. In terms of the group structure, so we have different brands based in different countries, kind of targeting different customer markets. So in the UK, where I'm based, we have a fast host internet, and then in Spain, Arcis internet. Had an interesting day yesterday with the power issues, which we thankfully survived. Also in Germany, Ionos, obviously the largest company in the group, and they're servicing customers throughout Europe and North America. As well as Strato, again, another kind of hosting and cloud business based in Germany, targeting Netherlands and Sweden as well. So yeah, in summary, we've got a broad portfolio of cloud and web solutions, and we're a market leader in Europe.
So, George, what did you do to open networking desegregation, and in general, why Sonic?
Right. So, I mean, historically, like most companies, we use traditional network vendors with vertically integrated hardware and software stacks. There are like well-known, limitations around that approach. Probably this is preaching to the converted, talking about it here, but in short, it's around a lack of flexibility, right? So when using a vertically integrated hardware and network and software network device, we can't then mix and match, right? So we can't pick which hardware we'll use per our requirements. We're kind of stuck with the vendor. And when you're quite widely deployed with the vendor inside the network, it can be non-trivial then to obviously change them out. They're often quite deeply integrated into your software ecosystems, internal tooling and such. So, for us, as a company, we've really got open source in our DNA from the early days. So it was a really appealing prospect being able to use an open network operating system, as well as open operating systems on the servers.
René, if I can ask, so you are our automate guru. How busy you were with our new automation which needed to happen with Sonic?
Mm-hmm. Yeah, first I'd like to guide you through the services which play a crucial role in our bootstrap phase of Sonic devices. So we have a centralized DHCP service, we have a file server, and a self-developed small ZTP API, and networks. Netbox plays the role of a single source of truth in that case. So we model the whole topology in Netbox and define all required parameters to render the full device configuration in config.db.json format. And the templates are rendered in Netbox directly, and engineers can observe changes directly via the front end. Our ZTP service acts as a facade to Netbox for Sonic, so it validates requests and is interfacing with Netbox, and the file server simply hosts the Sonic image, and the DHCP server, it has two fixed configurations. So one is for when a discovery request from ONI comes in, and one is for when a discovery request from Sonic comes in. So we don't maintain any device-specific configurations in these DHCP configurations. So we don't need to touch it when we onboard new devices, for example. Now let's dive into the bootstrap phase, step by step. Edgecore, thank you.
Edgecore devices, they come with ONI installed, get a management link, which has access to all the mentioned services. When ONI boots up the first time, it gets a temporary IP address from the DHCP server and a URI pointing to the Sonic image hosted on the file server. It fetches that image and boots Sonic. In the next boot phase, Sonic boots up, starts its ZTP phase, again gets a temporary IP address, and this time a URI pointing to that ZTP application. The ZTP application provides a sequence of instructions containing stuff like downloading the config.db file, some scripts, and execute these scripts and apply the configuration. And after that ZTP phase, the device is fully configured. So just to touch it slightly, during day 2, we wanted to leverage the same config.db files we used during the bootstrap phase. And Sonic doesn't natively support applying a target config.db file without disrupting device functionality. And to overcome this issue, we self-developed a service, an HTTP API, which we run as a container on Sonic itself. It is interfacing with Sonic via the switch service state software development kit and also RESTconf, and gives us the opportunity to apply a target configuration without disrupting the device. Yeah, that's it.
Kamran, maybe one for you. Thank you, René. So how does Enterprise Sonic support those kinds of use cases?
I think I'll start from the last. So René just talked about how they have this container running on the switch, right? So I think that once again the idea is that Sonic is a containerized architecture-based operating system, right? Sure. It gives you this capability that you can run your own container. So that's a big advantage for people like Ionos who want to leverage this functionality. At Broadcom, we've done a lot of features for Sonic. We are one of the largest contributor to Sonic and Psi project. One of the features that I'm very proud of that we contributed to community is something called UMF, Unified Management Framework. Kamal was talking about it earlier. This management framework is very flexible. It allows customer to access Sonic with a lot of open APIs. You can access Sonic using REST-conf. You can use it through GNMI, or you can access the same functionality through CLI as well. So there is a lot of automation capabilities inherent to Sonic, which can help with these use cases. Another thing is the monitoring capabilities. So for cloud providers like Ionos, it's very important to have very good deep visibility on the network to make sure that they are meeting their SLAs for their customers. And for that effect, we have a lot of silicon-enabled telemetry feature in Sonic, features like in-band flow analytics, features like mirror on drop, features like buffer statistics, which can predict, identify, and very quickly give you the root cause of the problem so you can fix it. So you can have a very high availability with Sonic. And finally, I think for any enterprise customer to adopt Sonic, ecosystem is very, very important. And that is where I think players like STORDIS come into picture, right? When many of these enterprise customers, they start their journey on open networking, they are not like Microsoft to just run community Sonic everywhere. They want to have a solution which is qualified, which has hardware which is qualified, which has optics which are qualified, and which has a support. If they know that if something goes wrong, there is somebody they can call upon, right? There is a single throat to choke if there is any problem. And that is where I was saying, you know, teams like STORDIS really come into picture. They not only provide very good support. I mean, we know that one of the largest telecom provider in Europe is Deutsche Telekom, which are running all of their 5G services on Sonic, supported by STORDIS. The things they do with, you know, for example, Monsoon, things we're doing with the Orca project. All of these things, I believe, they help in moving the needle for Sonic to make it more acceptable for enterprise customers. So the whole community really appreciate it, and thank you very much for your contributions.
Really appreciate. Now I don't know, you know, almost I lost my agenda, yeah? That was a little bit improvised. George, maybe going back, so could you tell us more about your infrastructure, but before the migration, and maybe the challenges which you've been facing? I'm sure that it was, you know, a little bit longer process. It was taking it didn't happen over a weekend.
It certainly didn't. No. It was a little longer than that. So before, you know, if I talk about maybe the previous network design based on InfiniBand. So we had an InfiniBand fabric. In fact, it was a dual fabric topology. So two separate, physically and logically separate networks. And we have compute and storage nodes that are taking a leg into each network for high availability. And we have then InfiniBand providing that like lossless, low latency connectivity that's needed for RDMA workloads. Touching on the Ionos Cloud Storage System, so it utilizes two kernel modules known as RNVD, which is RDMA over Network Block Device. So this was something that we developed internally at Ionos and upstreamed into the Linux kernel. And essentially, it is a pair of modules, one for the client, one for the server. And it takes care of mapping a remote block device. So, for example, you know, in our cloud setup, mapping the block device from a remote storage node and presenting it locally onto a compute node, like it's a local block device. And obviously, then we can mount VMs from that storage. So, you know, one of the main concerns for us was ensuring that in the new fabric based on Ethernet, that you know that protocol works well, and that's where kind of ROC EV2 really came into play. So thinking about maybe the traffic flows that we're seeing on the fabrics, you know, east, west, we've got this RDMA traffic for storage running from compute nodes to storage nodes. We also have overlay traffic, of course, going from between compute nodes where we've got customers with VMs that are in common private networks. North-south, obviously we have VM traffic, so customer VMs towards the internet, and here we have an issue, right? So when we are moving packets from the InfiniBand network northbound towards the non-InfiniBand network to get via the WAN to the internet, we have some requirements for intermediary conversion hardware, right? So we have these boxes known as internet gateways internally that are taking care of that decapsulation and encapsulation process. And with that comes an inherent bandwidth limitation. All right, there's only so much traffic that we can move through those boxes, and as well as bandwidth, there's also some complexity introduced in terms of architecting around potential failure modes there. So yeah, that bandwidth choke point and complexity was definitely a challenge that we wanted to try and overcome with the Ethernet design. Thinking about management traffic, so we had a dedicated separate management network, and we're plugging that into a management NIC on the hosts. We wanted to make some improvements there as well in terms of increasing the high availability and bandwidth by trying to converge that into the fabric, which wasn't an option on the InfiniBand setup. So, as well as those deployment-specific issues, there are also generalized issues, touching on vendor lock-in. Again, with InfiniBand, effectively NVIDIA is the only game in town. So when then we run into issues around, for example, long hardware lead times, that's a real pain point when you're trying to grow fast. There's not a lot of options. Obviously, in terms of TCO as well, like the actual cost of the switches and cables is a lot higher with InfiniBand versus Ethernet alternatives. And also the talent pool, right? So we're trying to find developers and engineers who've got that background in InfiniBand, and it's a relatively small talent pool, typically coming from the HPC kind of area. Whereas with Ethernet being so ubiquitous, it's a lot easier to find the developers and engineers that we need to help us design and operate the cloud. In summary, I'd say from our experiences, InfiniBand, it certainly fits well still, I think, to a number of low latency niche kind of use cases. But I mean, for general purpose, cloud workloads such as ours, Ethernet is a good fit, and increasingly so.
So, Jojo, how did you migrate to Ethernet, and what changes happened in your network design?
Okay, so I don't have a slide to support it, but if I just try and describe in brief like the network design as we have it. So there's nothing too exotic. We tried to stick with a relatively standardized topology. So it's a Clo fabric, it's 3-tier, 5-stage fabric with dedicated pods for different sorts of server connectivity. So we have dedicated pods for compute nodes and for storage nodes. And we also have a border pod design, so a dedicated pod where we'll have, for example, border leafs for external connectivity via the WAN, but also border gateways for stuff like VXLAN stitching between locations, if we want to do things like Cloud Connects, or for some migration use cases. Also, central services, so whether that's management services, but also for VNFs, right? So we have service leafs in that pod, and we have boxes that are plugged into those service leafs that are running VNFs, so customer firewalls, load balancers, those sorts of virtual appliances for customers. From a hardware perspective, it is right now edge core that we're using in the network, but the beauty of open networking is we can replace that out without facing too much pain if we like and when we like. We're using Broadcom Trident 4 across the board there, so we have 400 gig for fabric links, for switch-to-switch uplinks. And for the server-facing part, for the compute nodes, we're breaking those 400 gigs into 4 by 100 gig. And for storage nodes into 2 by 200 gig, so 200 gig NICs in the storage nodes. Obviously servers are dual-homed to multiple leases for redundancy. In terms of the logical design there, this is a pure layer 3 in the underlay, right? So obviously layer 3 in the network, but also layer 3 on the point-to-point links facing the hosts. And we are using BGP unnumbered there. If you're not familiar, it's essentially using just IPv6 link local addresses on all of the ports in the fabric, but also on the hosts. And we have then just a single BGP peering in one address family where we can transfer, advertise IPv4 and IPv6 prefixes, both with an IPv6 next hop. So there's quite a lot of simplification that we get in terms of automation and also operations. So we no longer have to deal with numbering transfer links. And because we are now, it's now pure Linux end-to-end, so we've also got Linux hosts also running FRR. So we're using a common approach throughout the network. Also, it's quite kind of plug and play, right, for the servers. They just kind of get plugged in and load the FRR configurations, and they're good to go with underlay connectivity. Touching on that management network. So as I said before, that was previously in a separate dedicated network. So we've now converged that into the fabric. Because we're using EVPN-VXLAN, so we have network virtualization now as an option. So we can carve that management network now into a separate namespace on the host, map that to a VRF in the fabric, transport it over the fabric, and then also into a mapped VRF in the WAN for inter-data center private connectivity, for example. Yeah, I mean, I think René already touched on the process for bootstrapping the switches, right, in terms of using ZTP and Netbox and all of that. The servers are also bootstrapped now via the fabric, so we're using DHCP relay on the leaf switches in conjunction with static Anycast gateway, and then relying on the EVPN-generated MAC IP host routes to steer the return traffic back from the centralized build servers to the appropriate leaf switch. For ROC EV2, I'd say, from a configuration perspective, in Enterprise Sonic, it was super simple. It's more or less a one-liner that then takes care of, creating all of the needed QoS configurations. And, importantly for us was that we didn't have to rework the RNBD protocol that we have to be optimized for Ethernet. Rocky took care of that, so we didn't have to then spend expensive developer time, reworking that whole software stack. So yeah, in general, also in our performance tests that the storage guys did, they saw a pretty much, I'd say, comparable performance with Ethernet when compared to InfiniBand. A couple of caveats maybe to call out is, when deploying this on Sonic, you need to take care that after enabling Rocky, the switch has to be rebooted. So obviously good to do that before it goes into production. And also around port breakout. So if you use port breakout as we do, then that can't be done when Rocky's enabled. So you have to take care of doing the right things in the right order of operations. But yeah, I mean, I would say in summary, for us, it's given us a nice simplified, standardized network architecture, highly scalable. And yeah, we've removed some of those problems that we previously had in terms of intermediary hardware and the bandwidth choke points and complexity that we faced, reduced cost overall, and just increased the simplicity of the solution end to end. So a lot of positives from our perspective there.
Thank you. Kamran, how do you see from your perspective? Are there also companies moving away from InfiniBand and more? It was already touched a few times, yeah? Everyone are talking about the latency, and always I remember that Fabric Internet, it's something with the lowest latency, or InfiniBand is with the lowest latency, and that was always like ideal solution for that AI and HPC. Could you, go deeper, but having in mind that counter, yeah, and explain how do you see that from your perspective?
Okay. So I think the two parts to the question. The first one is, do we see other customers moving away from InfiniBand and going to Ethernet? I think George articulated it much better than I can. In the cloud environments, everybody's moving away from InfiniBand for all the reasons that he articulated, right? You get much better performance, or at least similar performance at a much better cost point, and all the reasons that George articulated. So yes, for the cloud environments, I think no-brainer. Everybody's moving away from InfiniBand to Ethernet. Now, not everybody is as visionary as Ionos to choose, open networking or Sonic. There are customers who move to more traditional OEM vendors, right? But definitely moving away from InfiniBand to Ethernet. Now, is InfiniBand has advantage over Ethernet on latency? It's good that you're reminding me about the timer, because I can go on about it for a very long time. Short answer is, it's a lot of it is FUD, right? A lot of it is just marketing gimmick. I'll give you maybe 3 minutes and I'll try to explain that.
You have 5.
Oh, thank you. That's better. So, and we have, mostly it's a technical community, so I would love to answer this properly. Let's double click on this. So if you look at it from a face value, if you look at, there is something called fall-through latency. What is the fall-through latency? This is the latency of traffic going through a system. In this case, this is the latency of packet going through a chip. If you look at the fall-through latency of InfiniBand chip, it is around between 200 to 250 nanosecond. If you look at the fall-through latency of an Ethernet chip, it is around 600 nanosecond. If you just stop there and you get your marketing boys to start advertising this, you will say, wow, there is a 2 to 3 times better performance you can get with InfiniBand. That's not the reality. Let's double click on this. We are talking about fall through latency. That's one part of it. You need to send that data on the network, then it gets somewhere, right? We are talking about networking, we are talking about switching. So there is something called serialization delay. Now let's calculate serialization delay for any specific packet. Let's take an example of a 1 megabyte message size that you are sending on a very fast network. Now, what is a fast network we have today? Generally, it's 400 gigabit, right? So what is the serialization delay for a 1 megabyte message when you send it on a 400 gigabit link? So serialization delay is the time it takes to send zeros and ones onto the network, right? And that will depend on the link speed. I'm just going to do some very simple calculation here. Let me find the calculator. So we have a 1 megabyte message, which means 8 mega bits. Everybody agrees with me? Yeah, so 8 meg divided by 400 gigabit per second. So that is 400 gig is 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. The answer is 0.0002 second, which means 20 microsecond. So to send a 1 megabyte message onto network, you have a 20 microsecond serialization delay. 20 microsecond means 20,000 nanosecond. Now compare it. 20,000 nanosecond for serialization delay, add 200 nanosecond of InfiniBand or 600 nanosecond of Ethernet. It's less than 2%. It's actually 2% difference, right? But the reality is, when you look at AI application, there is no 1 megabyte message size there at all. That's like your email, right? In AI applications, the message sizes are reaching gigabyte. So if you look at a realistic AI application and you look at the message size, this difference between the fall-through latency, it becomes 0.000002%. It is totally negligible. But that is one type of latency. The more important latency, as I talked about earlier, and there is a papers written by Amazon and other people, the more important latency in case of AI environments is tail latency. That's where Ethernet is much better. The important metric in terms of performance for AI application is job completion time. Ethernet is at least 10% better in job completion time. So when you look at all of these metrics, you can say that these claim, maybe a good marketing claim, it has no legs to stand on.
No questions.
Thank you.
René, cool down. So what next? You automate already the Sonic-based fabric. What next? What you are looking for?
Yeah, we want to improve the visibility of our network health, and by deploying Monsoon on our Sonic devices, we don't have that yet, and integrate it with our monitoring solution. So that is one part. The other is, as I think George mentioned in the beginning, we are using Enterprise Sonic at the moment. And the logical next step forward is to look into the build process of Sonic and to finally shift to community Sonic. Yeah, that's.
George, anything to add?
Yeah, I guess I would add, as I mentioned in the beginning, what's coming next. Well, right now, the team's working super hard on building out our first public cloud on Ethernet in Frankfurt as we speak. So yeah, looking forward to getting that launched. And then after that, you can guarantee there will be more. So the next location is also coming on Ethernet, and we'll obviously be optimizing our design and enhancing it as we move on. Also, I mean, that's in the context of our public cloud, but we have many other different network designs for other products and platforms, and we'll be looking to try and consolidate and move those onto our strategic network design moving forwards. So yeah, there's lots to come there.
Kamran, maybe one back to you. So how Ethernet evolving to support AI and modern workflows? Everyone is talking about the AI, so
I would say Ethernet is already the de facto standard for AI, in my view. I already talked about 7 out of 8 megascalers. What do they use for their AI infrastructure? They use Ethernet, right? So Ethernet, and I already talked about the scale of the networks, right? I talked about 100,000 GPU cluster that Alibaba built based on Ethernet. We are working with another customer who are building 250,000 GPU cluster, right? All based on Ethernet. But where we want to go next on the Ethernet side is that we want to be able to build, we want to be able to support a 1 million GPU cluster. We don't know who's going to build it, but we want our network to be able to support it. And for that, Broadcom got together with 9 other companies a couple of years back where we formed this Ultra Ethernet Consortium. Right? I think most of you have heard about Ultra Ethernet Consortium. There's been a lot of work ongoing at Ultra Ethernet Consortium, and the output of this work will be specifications, like we have IEEE 802.3, like those, right? So the UEC specification, that 1.0 version, is expected to come out in the next month or two, right? Most probably in May. And with UEC, you will see that we will be able to support very, very large clusters. Now, if you ask me, what we're doing in UEC, there is a lot of work ongoing. If I just give you one pointer here, the most impactful work done at UEC, in my opinion, is that we are modernizing RDMA. Remember I talked about RDMA has a lot of inefficiencies, right? RDMA enforces you to do in-order packet delivery. RDMA has a very inefficient retransmission algorithm. RDMA does not support multipathing, and so on. We are going to fix all of these issues with Ultra Ethernet Consortium. And I believe that with UEC, not only that we will be able to scale AI clusters to 1 million GPU, I believe with UEC, Ethernet will become an even more attractive option for HPC workloads as well. So I do see that there is a strong possibility that going forward, SONiC will become a dominant player, a dominant network operating system, not only in the data centers, but also in HPC and AI environments as well. Thank you.
Oh, thank you. So let's maybe open the flow, and we can also ask our guests. We have still a few minutes, so just raise your hands and we will bring the mic.
Hi, interesting discussion. I'm just curious, I suppose, for the guys here who have deployed. You're talking about moving from an enterprise SONiC to a community version. Is that based on the enterprise code being rebased into community over a period of time that you're satisfied that that then has the features? Or is there a reason why you didn't start with community from the outset specifically? And is that based on the expertise with STORDIS? Sorry if that's a bit of a long question, but...
No, it's a good one. Yeah, no, it's a good question. I can maybe start with the second part of it. So why did we start with the enterprise SONiC? I think basically, it's given us a nice fast start, right? We've got certain guarantees there in terms of, the backing that we have and also the features that are there that we need. So, it was really for us about velocity, about getting there quickly enough. Longer term, we want to avoid any kind of a lock-in, and that includes also at the ASIC level. So we do want to ensure that we're able to truly own our own destiny, which is the promise that would come with the community SONiC. So that's where we want to get to eventually. But I think it would have probably been a push too far to try and be there from day one. We already did have community SONiC, and we do have community SONiC deployed internally for some more simple, like IP routing use cases, and we have had for some time, right? So it's not unknown territory to us. But in terms of deploying our full public cloud stack with all of that, ROC EV2, etc., that's really where we had the need for enterprise SONiC in the beginning.
So silicon diversity then is kind of the driver in terms of effectively.
Yeah. And also just we want to be able to see all the source code, right? We want to have full open source. You want to have control of all of the source code and visibility of all of the source code.
Thank you.
Okay.
Any further questions?
So if you don't have any questions, I would like to really provide like a great thank you to our brave guys. We know how stressful it was. We've been trying to prepare ourselves what we can maybe feel, but it is great to see like just a real use case, yeah? So, okay, maybe we've been trying to manage that discussion in a more professional way, but what is beauty, it's simply the daily work. And again, it was not happening over a weekend. I remember our first meetings, first discussions, starting from the community zoning, facing some challenges and so on. This is why today we are with the enterprise, but as you say, and the question was, it's not locking us with first hardware, second, any of those enterprise version, yeah? In the end of the day, even, I strongly believe that one day the community will be stable enough that you can go to the full production, yeah? We will be still friends, Kamran, yeah? But definitely, so really big thank you to our guest, big applause, and appreciate it.